Welcome back to the deep dive. We're circling back today to something we've touched on quite a bit recently.
That's right, the Ganitapada.
Exactly. Those, 33 verses from Aryabhata's Aryabhatiya, way back in 499 CE.
An incredible piece of work. And, for listeners who've been with us, we've already looked at some key parts, haven't we?
We have. We got into the kuṭṭākāra,
The pulverizer.
the whole decimal system revolution, his ideas on eclipses, even how market sequences might connect.
It's really fascinating stuff. So I guess today is about kind of weaving all those threads together, seeing the bigger picture of the Ganitapada.
That's precisely the idea. This is the finale for our Ganitapada exploration, really pulling it all together based on, well, all the interest and the notes we've gathered.
Okay.
We want to expand on it, get into the history behind it, maybe dig a little deeper into the math itself, trace how these ideas spread across the world, and crucially, why they still matter now.
Sounds like a plan, a proper deep dive into its legacy.
So let's set the scene. Imagine the Gupta court, 499 CE. Power, culture, but also problems.
Right. And the big one seems to be this new tax edict from the emperor.
Yeah, our sources suggest this wasn't just a minor adjustment. It sounds like it really shook things up.
Well, think about the practicalities back then. How do you actually implement a large-scale tax change fairly? Measuring fields, assessing value.
Especially with the tools they had. Probably quite basic, right? Lots of estimation.
Exactly. You've got diverse lands, different crops, variable weather. Trying to apply a uniform rule could easily lead to, well, chaos, inconsistencies, maybe unfairness, certainly anxiety among the population.
You can see how it would cause real problems.
Definitely a recipe for confusion, at the very least.
Okay, so into this tense situation steps.
A student.
A young scholar, yeah, Devadatta, a student of the great Aryabhata himself.
But he's not leading protests or anything like that. His approach is different.
Very different. His weapon, so to speak, is the Ganitapada, those 33 verses on a palm leaf manuscript. The sources call it a rebellion of numbers. I love that phrase.
It is evocative, isn't it? It suggests using intellect, using mathematics, to challenge maybe a heavy-handed decree.
Pitting reason against raw power, in a way.
Precisely. It highlights that math isn't just abstract, it's a tool for solving real problems, even complex social and economic ones, a force for order, maybe even justice.
So how did he actually use these verses? Our notes mention specific ones.
What's really clever is how targeted it seems to have been. He apparently picked specific mathematical tools for specific parts of the tax problem.
Okay, like what? For measuring land, for instance. That
Yeah.
sounds like a huge task.
Right. So for land area, he supposedly used verse 6, the formula for a triangle's area, half base times height,
Familiar stuff.
and verse 8, which helps calculate the area of a quadrilateral.
Ah, so breaking down complicated fields into simpler shapes. Triangles, four-sided figures.
That seems to be the idea. Makes it systematic, less arbitrary than just, guesswork.
Okay, that standardizes the measurement part. But fields can be huge. You can't measure every square inch.
True. And that's likely where verse 26 comes in the rule of 3.
Proportions.
Exactly. Measure some representative sample plots accurately, then use proportion to scale that up for the larger area. It's efficient.
Makes sense.
Yeah.
Much more practical. What about other resources? Water's crucial for farming.
Absolutely. And for things like circular wells, verse 10 would be key. It gives that remarkably good approximation for 3.1416.
So they could calculate the capacity of wells accurately.
You'd think so, yes. Understanding water resources would be vital for judging land productivity and therefore its fair tax value.
Okay, land area, water. What about boundaries? Surely land disputes were common. How did math help there?
This is really ingenious. Verse 14 deals with shadow measurements.
Using shadows. How?
By measuring the shadow cast by an object of known height, like a gnomon, a vertical stick at a certain time of day, you can use geometry, basic trigonometry really, to calculate angles and distances.
So you could map out boundaries.
Without actually having to walk all over the crops or trespass. Non-invasive surveying.
That is clever. Using sunlight and simple geometry. Okay, measurement covered. What about the tax burden itself? The money or the grain?
This is where it gets into fairness and people's ability to pay. Devadatta might have pointed to verse 25.
What's that one about?
Interest calculations.
Interest, so like payment plans.
That's the implication, yes. Maybe allowing people to pay their taxes over time with some calculated interest rather than demanding it all at once right after harvest, perhaps. Makes it more manageable.
It feels surprisingly modern, spreading the load.
It shows a sophisticated awareness of economic reality, doesn't it? and if taxes were paid in kind with grain.
Which must have been common.
Very.
Yeah.
Then, verse 29 on mixture problems becomes important.
How so?
It allows for fair assessment when you have mixtures of different qualities or types of grain. You need a mathematical way to calculate the value consistently. It prevents arbitrary judgments.
Standardizing the tribute value. Makes sense. Right. Okay, and we can't forget the big one we discussed before, the kuṭṭākāra, verses 32 and 33. How does that fit in?
The pulverizer. Its strength is solving indeterminate equations, finding whole number solutions where there seem to be many possibilities.
Like finding cycles.
Exactly. It could be used to synchronize things, like aligning the timing of harvest cycles when farmers actually have produce or income with the tax collection deadlines.
So farmers aren't forced to pay before they even have the means.
Precisely. It aims for a more sustainable, less disruptive system.
So Devadatta basically presented a whole mathematically based system. More efficient, potentially fairer, more predictable.
That's the picture painted by our sources, yes. A logical framework contrasting with perhaps a more haphazard approach.
And the emperor apparently reacted positively.
The accounts suggest he was impressed. Whether it happened exactly like that is maybe debatable, but the story itself is powerful.
It really is. It shows math not just as calculation, but as a tool for, well, for justice, for hope even.
It elevates the Ganitapada beyond just formulas. It becomes a symbol of reason applied to societal well-being.
A great story to start with. Let's shift focus now to Aryabhata himself, back in Kusumapura. Creating these 3 verses. This wasn't just a random list, was it?
Oh, absolutely not. That's one of the most remarkable things. The Ganitapada isn't just a collection of handy rules. It's a system, deeply interconnected.
You can see the logic flowing through it.
Definitely. The verses build on each other. It shows a really coherent, systematic, mathematical mind at work.
Can we trace some of those connections? We touched on this before, but maybe highlight a few examples.
Sure. Take verse 2. The decimal place value system. Ika, dasha, shada 1, 10, 100.
The foundation.
Absolutely the foundation. Without that clear, efficient way of writing and manipulating numbers, almost none of the other calculations in the Ganitapada would be practical or even possible in the same way. It was a huge conceptual leap.
Right. Everything else relies on that base 10 system. What's another link?
Well, think about pi. That value, around 3.141 seen, mentioned in an earlier verse.
The one Devadatta used for the wells.
Exactly. That understanding of circles and spheres is fundamental. It doesn't just help with wells. It's crucial for Aryabhata's astronomy, calculating areas, volumes, understanding orbits. One constant unlocks so much.
Okay, so connects geometry on Earth to the cosmos. What about those shadow measurements from verse 14?
Those aren't just for surveying fields either. The underlying geometry, understanding angles, proportions, the seeds of trigonometry, that's the same mathematical toolkit Aryabhata used for his astronomy.
Like predicting eclipses. We covered that.
Precisely. Predicting eclipses relies on that same understanding of angles and geometric relationships derived from observing things like shadows. So mapping a field and predicting an eclipse are linked by the same core math.
That really shows the integration. Practical and theoretical feeding each other. What about the sequences? We talked about them for merchants.
Right. Sequences and series. They help analyze patterns, growth, change useful in trade, maybe finance. But the principles behind sequences, the idea of ordered progression, also underpin some of the algorithms used for calculations elsewhere in the Ganitapada. It's part of the overall logical structure.
And the kuṭṭākāra again. That advanced concept we now link to crypto. Where does it fit in this web?
It comes near the end, but it's not isolated. Its core ideas, modular arithmetic, finding integer solutions, they relate back to fundamental number properties that are implicitly used throughout the text. Thinking about cycles, remainders, that's relevant to basic arithmetic and complex problems like synchronizing cycles or, much later, cryptography.
It really paints a picture of a unified mathematical vision, not just tricks, but a whole system.
Exactly. And it's interesting, Bhaskara first, a commentator writing a couple of centuries later, he described the Ganitapada as both divine and practical.
Divine and practical, that captures it perfectly, doesn't it? Reflects that Gupta-era mindset.
It does. This idea that math could reveal something about the cosmic order while also being incredibly useful for everyday life.
Aryabhata saw numbers linking everything. Altar to orbit, shop to sky, as one source put it.
A beautiful way to phrase it. And this vision, this mathematics, it didn't just stay in India, it spread.
Right. Let's trace that journey. How did these ideas travel?
The decimal system, verse 2, again, was probably the biggest export early on. By the 8th century, maybe earlier, it reached Baghdad.
The intellectual center of the Islamic Golden Age.
Exactly, a melting pot of ideas. And scholars there, like the famous Al-Khwarizmi.
His name gave us algorithm.
It did. He wrote a key text essentially called On Indian Calculation. He saw how powerful the Indian system was, especially with the concept of zero shunya.
Which wasn't really a feature in, say, Roman numerals.
Not in the same functional way. Al-Khwarizmi's work was crucial in spreading these Arabic numerals, though they originated in India throughout the Islamic world.
And eventually they made their way to Europe.
Yes, but it took time. A key figure there was Fibonacci in Italy.
1202, his book Liber Abaci.
Right. He'd learned the system probably in North Africa from Arab merchants or scholars and strongly advocated for it in Europe. He showed how much easier it made calculation, business, everything.
But it wasn't an overnight switch from Roman numerals.
Not at all. It took centuries. Think about doing long division with M's and C's and X's.
Oh, wow. Yeah. CCCV versus 305. No contest.
It's hard for us to even imagine now the decimal system is so fundamental, but it was a slow revolution.
And it wasn't just the numbers 0 through 9 that traveled, was it? What about pan and trigonometry?
Those traveled too. Aryabhata's value for pan and his early work on signs, the Jaya tables, were incredibly important.
How were they used?
Arab astronomers built on them heavily. They needed accurate trigonometry for things like calculating the precise direction of Mecca, the Qibla, from anywhere in the world.
Vital for daily prayers.
Absolutely. And later, in Europe, people like Regiomontanus developed much more extensive trigonometric tables based on these foundations. These tables were indispensable for the age of exploration.
For navigation, cartography.
Exactly. You can't navigate accurately across oceans without good trigonometry. So Aryabhata's work indirectly fueled that whole era of global discovery.
Amazing. And back to the kuṭṭākāra. You mentioned cryptography. That connection seems almost unbelievable.
It's pretty stunning. The mathematics behind the kuṭṭākāra is essentially what we now call the extended Euclidean algorithm.
Okay.
And that algorithm is a core component of RSA encryption.
The security stuff used in online banking. Secure websites.
Yes. The very same mathematical logic developed to solve problems about cycles and remainders in 5th century India is now protecting our digital transactions. It's a direct, albeit long, lineage.
That's genuinely mind-bending, from harvests to HTTPS.
It really is.
Even the shadow measurements found later use.
Oh, yes. The principles of using shadows in geometry for surveying, described in verse 14, continue to be refined. They inform techniques used historically in places like Damascus and Delhi for mapping and construction. The core idea has had lasting practical value, even feeding into modern techniques involving remote sensing and drones.
It's incredible how adaptable these core ideas are. Our sources even suggest Aryabhata's logic underpins things like GPS, blockchain, AI. That sounds like a huge claim.
Well, it's maybe not a direct line like with RSA, but the kind of thinking is foundational.
How so?
The ability to model the world with numbers, to think algorithmically, to reason logically about complex systems, all things evident in the Ganitapada, are absolutely fundamental prerequisites for technologies like GPS, which relies on precise timing and geometry, blockchain cryptographic principles, and AI, pattern recognition, logical inference. Aryabhata helped lay the groundwork for the mathematical language our modern world speaks.
Which brings us right back to the present. Why does this ancient text, the Ganitapada, still resonate? Why should we care in, 2025?
Because its impact isn't just historical, it's ongoing. We use the decimal system constantly. Engineers and scientists rely on our daily. The kuṭṭākāra's descendant secures our online world. Shadow principles still inform measurement. It's not abstract history, it's embedded in our modern reality.
But it's more than just the practical applications, right? There's a deeper significance.
I think so, yes. Aryabhata didn't just give answers, he demonstrated a way of thinking. Using numbers and logic to find order, to understand patterns, whether in the heavens or in human affairs, that approach itself is timeless.
It connects his world in 499 CE directly to ours. That vast span of time just collapses.
It really does. And you can appreciate the Ganitapada in different ways, too.
How do you mean?
Well, an engineer might admire the sheer elegance and efficiency of the mathematics. A Sanskritist might appreciate the poetic structure and precision of the language itself.
And for the rest of us?
For everyone, I think, there's inspiration in the story. The power of human intellect to decode the universe, to ask questions, to find harmony. It's a call to keep exploring, keep understanding.
Threads of eternity. One source called the verses. That feels right.
It does capture that enduring quality.
And this isn't even the end of the Aryabhatiya itself. The Ganitapada is just one part.
Exactly. It's the first of 4 sections. We've briefly mentioned the others before, the Kālakriyāpāda on time and the Golapada on the celestial sphere. Still more to explore there.
Well, this has been quite the journey through the Ganitapada, from Devadatta using math as a form of defiance in the Gupta court.
To tracing its incredible path across continents and centuries right into our modern digital lives.
It's really highlighted that these 33 verses are so much more than math problems. They're about ingenuity, observation, maybe even a form of rebellion, a kind of poetry, and definitely survival of ideas.
Well said. They demonstrate this deep human drive to understand, to calculate, to find order, and how powerful that drive can be.
So where does our next deep dive take us? You mentioned the Kālakriyāpāda, time itself.
Yes. Next time, we plan to get into Aryabhata's reckoning of time, his calculations of cosmic cycles, planetary periods. He developed a system that was astonishingly sophisticated for his era.
Predicting planetary movements, defining units of time.
Exactly. His work on timekeeping and astronomical prediction was revolutionary.
It makes you think, doesn't it? About time itself. Is it this fixed, objective thing flowing past us that we just measure?
Or is our very concept of time shaped by how we measure it, by the mathematical models we build, like Aryabhata did?
That's a deep thought to leave us with. Is time out there, or is it partly in here, in our understanding?
A good question to ponder. Until then, we hope you, our listeners, keep digging into these connections between the past and present. Keep decoding the ancient world.
And keep applying that knowledge to shape the modern one. For the deep dive, thanks for joining us on this exploration of the Ganitapada. We'll connect again soon.